Hi, this presentation describes the Oracle Database 18c server architecture. The Oracle RDBMS consists of structured data and a memory and background processes. The memory and the background processes together are called an instance. When an Oracle instance is started, the memory structures for System Global Area or the SGA and the Program Global Area or the PGA are allocated. The SGA memory contains information necessary to manage the database. It consists of additional component memory structures such as the shared pool, library cache, large pool, database buffer cache, and so on. The PGA contains the necessary information to manage the server processes and background processes. Structured data is stored in files on disks. Data is arranged in a proprietary relational format consisting of tables and columns. Some data can also be stored as external files, which could be binary large objects or flat files, etc. Background processes include system monitor, process monitor, database writer, and other processes which perform I/O and various tasks to monitor database operations. The Oracle Multitenant Architecture is designed to support many pluggable databases and one root container database or CDB. For example, one root container database can have many application databases such as sales, HR, order entry. The traditional non-CDB database contains only one database. Many applications can be supported on it using the schema-based approach. The Oracle Multitenant Architecture contains one set of background processes and one SGA. Each container database contains one or more pluggable databases and/or application containers. An application container is an optional pluggable database which may contain one or more pluggable databases of a particular logical application data model. The application container hosts the shared metadata, data, and code. An application container is like a root container for its pluggable databases. The multi-tenant architecture presents many advantages over traditional non-CDB databases in terms of consolidation, manageability, separation of data and code, performance tuning, patching and upgrades, and ease of data movement. Pluggable databases have their own system sysaugs and other user table spaces. When using local undo management, each PDB also has its own undo table space. Similarly, temporary table space can either be shared or each pluggable database may have its own temporary table spaces. The Oracle Sharding Architecture provides linear scaling via horizontal partitioning across multiple databases. Each of these databases reside on separate servers. Each server contains its own CPU, memory, and disk. Its benefits also include fault containment due to the fact that it eliminates single point of failures such as node, disk, memory bottlenecks, and the rack clustering. Sharding architecture provides data containment within the geographical boundaries of a particular region if needed for regulatory requirements. Sharding is easy to deploy in a cloud or on-premise. Client requests are routed through a connection pool. The connection pool contacts one of the sharding directors or network listeners. The listeners directs the client request to the appropriate shard. Oracle Database physical storage consists of various types of files. Database file types include data files and temporary files, control files, and online redo log files. Data files are used to store tables, indexes, materialized views, and data dictionary information. Data is written in Oracle proprietary format and cannot be read by other programs. The control file stores information about physical structure, checkpoint position in the online redo log files, and changes made to the files of a database. A control file is required for the recovery of a database. When the data file is added or deleted, the control file is updated to reflect the change. It is recommended to have more than one copy of the control file to provide redundancy. An online redo log file stores all the transaction records and changes made to structure of database objects. The number of redo log files depends upon the number of database transactions. The redo log file should be multiplexed to protect against losing one of the files. Oracle Database stores data in the data files on physical disks. Space is allocated as data blocks in a particular table space. Data block size for a database can vary. Standard block size is 4K or 8K and cannot be changed unless the database is recreated with a different block size. A data file belongs to one particular table space. A table space is a logical unit of allocation. For example, a table space may contain only indexes for a particular application, or one which may only contain tables. System and sysaux table spaces are mandatory and created by default for each pluggable database or a non-CDB database. A table space may be created with a non-default block size. Table spaces contain data segments. Types of segments could be table, index, clob index, etc. And each segment comprises multiple extents. Each extent belongs to a single data file, and extents always belong to the same table space. Oracle database processes can be classified as client processes, background processes, and server processes. Client processes originate from clients such as the web client, SQL Plus, or JDBC connecting to a database. Background processes are Oracle Relational Database Management System processes, which perform various database management functions such as disk I/O, memory management, process monitoring, and job scheduling. Server processes communicate with the database processes to complete client requests. In a dedicated server, each server process exists as a separate OS process, which performs the client requested work. In a shared server, one process may serve more than one client processes. An Oracle database instance consists of a memory structure and a process structure. The memory structure components are System Global Area, or the SGA, and Program Global Area, or the PGA. The SGA contains memory structures which are shared and maintain data and DBMS management information. The database buffer cache, which is the data memory area, is a part of the SGA. The redo log buffer, which keeps a record of all the transactions in the database, is also a part of the SGA. There are other memory structures for the relational database management system which comprise the SGA. The PGA is used by each Oracle process on the server. This includes background processes and server processes. Each process has its own PGA, which includes information about the session, sort area memory size, hash area, and so on. Oracle Database supports the client-server architectures, wherein the application client typically runs on a separate machine from the database server. The clients could also run on the same server as the database, but separate machines allow for better performance. Oracle Database also supports multi-tier architecture, wherein, in addition to clients and server machines, there could be one or more application servers which serve up the HTTP requests from web-based clients. Oracle Database also supports the service-oriented architecture in offering the request response model as an autonomous service. Let's view the memory structure System Global Area, or the SGA, in detail. The SGA consists of a shared pool the large pool, database buffer cache, fixed SGA, the Java pool, streams pool, and the redo log buffer. The SGA can optionally contain an in-memory column store area starting with Oracle 12c. So the SGA is a group of memory structures which allow for efficient management of the relational database system. The system global area memory is allocated when the instance is started. The memory is reclaimed at instance shutdown, and every instance has its own SGA. We will explore each of the structures as we progress. So let's take a closer look at the system global area, specifically the shared pool. The shared pool consists of the library cache, which contains the shared SQL area, and the private SQL area. The private SQL area is used only if the installation is in a shared server configuration. In a dedicated server configuration, the private SQL area is a part of the PGA. The other important shared pool components are data dictionary cache, server results cache, and the reserved pool. The library cache is a memory structure in the shared pool which is used to store SQL statements, SQL query execution plans, and parsed and compiled PL SQL code. Locks and library cache handles are also stored in the library cache. The database attempts to reuse compiled code or SQL execution plans already present in the library cache. If the SQL statement or execution plan is not present in the library cache, the DBMS creates a new version of the SQL or execution plan. The efficiency of the library cache is determined by the number of hits or number of times a SQL statement was found in the cache versus cache misses or the number of times a hard parse was required. The shared SQL area contains all SQL statements which have been executed and shares the code and execution plan of SQL statements amongst all sessions. An execution plan is the steps the database optimizer takes to retrieve query results. Each user session has a PGA or a private global area. The private global area contains pointers to the shared SQL area. If the user session finds an identical SQL in the shared SQL area, it uses it to execute the statement, and if no identical SQL statement is found, then allocation is made for the SQL in the shared pool. So it becomes significant to try and reuse SQL code in order for the library cache to be efficient. In a shared server configuration, the library cache also contains private SQL areas of user sessions. The executable code which reside in the library cache comprises PL SQL programs and Java classes and is referred to as program units. Shared pool memory is allocated when a SQL statement such as an insert, update, or delete is parsed. Shared pool memory is managed using the least recently used algorithm. Space is freed only when it is needed for new items. To remove the contents, all the contents of the shared pool, alter system flush shared pool command can be executed. Changing the global database name will also flush the shared pool. The data dictionary cache holds information about the structure of the database and all objects contained in the database including users. This type of cache is also known as row cache because data is held as rows instead of buffers. Data dictionary information is also shared in the library cache. When a SQL statement or PL/SQL function is executed, the database returns results and stores them in the server results cache. When a SQL query or a PL/SQL function is executed, the database looks for the results in the results cache. If found, it uses the results from the memory or the results cache. Otherwise, it executes the query and fetches the results and stores the results in the server results cache. A SQL statement can be written with the results_cache hint to store query result in the SQL query result cache. The initialization parameter result underscore cache underscore mode determines whether to store the result of all the queries in the cache or only when a hint is used. Reserved pool. Oracle database can allocate large chunks of memory, contiguous memory, for objects which are larger than 5K. By allocating chunks in the reserved pool instead of contiguous memory, the database avoids running out of memory due to shared pool fragmentation. The initialization parameter, shared pool reserved size, is used to allocate the memory for the reserved pool. The reserved pool performance can be viewed using the data dictionary view $shared underscore pool underscore reserved. The value of the request misses should be as low as possible for reserved pool to be most efficient. So let's move to the system global area, or the SGA, which comprises the shared pool which was just discussed. Let's move to the large pool now. Large pool is reserved for memory allocations which are too large to fit into the shared pool. This includes Recovery Manager or RMAN IO slaves, message buffers used in parallel execution, user global area for shared server, and buffers for deferred inserts. Unlike the shared pool, which uses the least recently used algorithm to free buffers when it needs memory, the large pool memory is released when the session releases it. Shared pool can become fragmented by contiguous memory allocations. The database avoids the shared pool problem by allocating memory from the large pool. When you're not using automatic memory management, the Oracle database allocates memory for parallel operation message buffers and RMAN IO slaves. To avoid negative impact, it is recommended to use automatic memory management to ensure that the large pool will be used for parallel query execution buffers. The large pool is not configured by default. Oracle recommends using the large pool for UGA in a shared server architecture. UGA is the user global area and it is the memory required for a particular session. It stores information about the session state. If the large pool is not configured, the database uses the shared pool to allocate memory for the UGA for a shared server architecture. It is recommended to use automatic memory management to ensure that the large pool is used for parallel query memory buffers. The $sesstat view contains information about the user's session memory. The statistic session UGA memory shows the amount of UGA bytes allocated to the session. The session UGA memory max shows the maximum amount of memory in bytes ever allocated to the session. The database allocates buffers for deferred inserts from the large pool. With the advent of high computational power, modern applications such as Internet of Things or IoT applications receive data at a high frequency. For example, for a stock trading application, there may be a large number of transactions for trading, price change, quote, etc. The amount of data collection can be quite large and could create I/O bottlenecks on the database server. To address this problem, applications can use a hint and insert rows into a table specified as mem optimized for write. The deferred write buffers use a memory area in the large pool which buffers the inserts and writes them asynchronously to disk in the background. The database creates an array of buffers on the server and the space management coordinator and its helper processes write the array to disk asynchronously using standard data block format. A notable point here is that the writes cannot be rolled back as the data is written directly to disk. Client applications which do not allow data loss should maintain a local copy of the data after writing to the large pool. The in-memory column store is an optional area in the SGA which stores database tables, partitions, and materialized views in columns. The in-memory feature, combined with the storage, help improve the performance of reads, joins, and aggregations. The database buffer cache is the component of the SGA which stores the data blocks. The Oracle database bypasses the buffer cache for some operations such as sorts and parallel reads. The dynamic performance view v$db_cache_advice provides insight into the database buffer cache performance. The statistics, cache hits and cache misses are used to compute the buffer cache hit ratio. To use the v$db cache advice view, the initialization parameter db_cache_advice should be set to on. The buffer hit cache ratio should be sized based on SQL query optimization and other performance considerations. While a high buffer cache hit ratio may wrongly indicate that the cache is sized correctly, a low ratio may not indicate otherwise. The DBA can configure the database buffer cache based on factors such as frequency of a SQL statement, SQL design, and full table scans. The db_cache_size parameter specifies the cache size for the database standard block size. Users can create table spaces with non-default block sizes for performance reasons. In such cases, separate caches of various block sizes can be created. The initialization parameter db_cache_size is used to configure the size of the database buffer cache. The buffer cache is managed using the least recently used algorithm. Usage patterns of the database buffer cache vary based on the type of load. For example, a batch job run only once a day versus a transaction which is run many times a day. The transaction table might benefit from keeping the data in the segments in the memory, while the space used by the batch job can be recycled for other uses. Oracle database provides multiple buffer pools to address these irregularities. The keep buffer pool can be used to keep some objects permanently in the memory, and the recycle pool prevents objects from consuming too much memory space. Buffer pools are managed using the least recently used algorithm. The goal of the database buffer cache is to reduce or eliminate disk I/O. The v$db_cache_advice view provides information and advice on the database buffer cache. Some of the other components of the system global area are the redo log buffer, the fixed SGA, the Java pool, and streams pool. The redo log buffer is a circular buffer which stores redo log entries which contain all changes made to a database. The redo log buffer is used to hold the changes until they are written to disk to an online redo log file. The fixed SGA is used internally by the database. It maintains the database and instance state and information about locks. In a dedicated server connection, the Java pool contains all the shared Java code but not the user session state. The shared server configuration, the Java pool includes shared Java code and some UGA session state information. The database contains a Java pool advisor which can be switched on by setting the statistics_level parameter to typical or higher. The streams pool stores the messages of buffered queues. Oracle background processes can be classified as mandatory, optional, or slave processes. Mandatory processes include the PMON, SMON, RECO, MMON, MMAN, DBWR, CKPT, LGWR, and LREG. Optional processes are the ARCN, the CJQ0, JNNN, FBDA, SMCO, and RVWR. Slave processes are helper processes for other processes such as IO disk IO slaves and parallel query slaves. Let's see some details on Oracle background processes. Oracle background processes include the ones listed on the screen, but they are not limited to these. Depending upon the Oracle feature being enabled, more background processes may be present. For example, if real application clusters are being used, then global enqueue service monitor process, instance enqueue process, global enqueue service monitor will also be present. If Oracle Flashback database feature is enabled, the recovery writer process or RVWR will also be present. The process monitor or the PMON is responsible for the monitoring of processes and cleanup of the buffer cache and resources used by a client process. Cleanup includes locks, process IDs, etc. There is a cleanup main process or CLMN and helper processes or CLNN. The PMAN process or the PMAN manages other processes including shared servers, pooled servers, and job queue processes. It starts and stops the dispatchers in the shared server, connection broker, job queue processes, and restartable background processes. The listener registration process, LREG, communicates with the Oracle NetListener and database instance and dispatcher processes. It periodically contacts the listener and updates information regarding instances and services. The SMON system monitor process performs system recovery when instance fails. It also performs cleanup if one of the processes fails. The database writer process or the DBWR writes contents of the database buffer cache to disk. The log writer or the LGWR process writes the redo log buffer to the online redo logs on disk. The checkpoint process or CKPT signals the database writer process to write modified database buffers in the buffer cache to disk periodically. It updates the control file and data file headers with a checkpoint position, SCN, and location in online redo log where instance recovery must begin. The recoverer process, RECO, is used to resolve distributed transactions which are pending in case of system failure in a distributed database. The MMON and the MAN or the manageability monitor light processes. These processes monitor metric thresholds, generate alarms, and write statistics from the SGA active session history to disk. The archiver process, ARC, is a background process which archives the online redo logs when the database is in archive log mode. Archive redo logs are used for point-in-time recovery of database. This brings us to the end of this presentation. Thanks for watching. For more information, please see Oracle Books online.